Hello students, in this session we are going to study the thin spherical shells. That what are the stresses developed in thin spherical shells? Like we have already studied about the cylindrical shells, now we want to study about the thin spherical shells, right? So a sphere is a sphere. Cylinder has two types of dimensions, that is longitudinal direction and circumferential directions. Here sphere is a sphere, so it has same dimensions on all sides, right? So suppose this is our sphere. So in both directions, hoop direction, there is hoop direction, and the stresses developed are same in both the directions. So suppose this is the, like this, we are making a sphere like this, and we want to show the hoop stresses in this material, right? So there all directions are hoop directions in this case, like this. So these are the hoop directions. So this is the hoop stresses developed in the material, right? And these hoop stresses are developed due to the pressure applied on the area, this area, that is the internal dia. Some internal dia is there, and the pressure developed is, suppose P. So P is the pressure developed in the material, pressure applied by the fluid, that is the internal pressure applied by some external fluid, that is P, right? And this pressure is applied on this area, internal diameter, and the internal diameter is given to us, and this is the thickness of the material. So internal diameter is given to us, this is D, and thickness is T. T is the thickness of this sphere, right? So T is the thickness of the sphere, D is the internal diameter, and pressure is acting on the internal diameter. So we will take the projected area on which this pressure is acting, and hoop stresses are developed in this direction, right? So for static equilibrium, the forces due to this pressure, pressure multiplied by the area on which this pressure is acting, that is the projected area of a sphere when seen from the top view, that is pi by 4 d square, that should be equal to the area of this ring, that is equal to sigma h multiplied by the circumference pi d multiplied by t, pi dt, right? So this is the area of this ring, if we talk about the ring at which these hoop stresses are acting, right? So finally you will get sigma h as pi to pi cancel, d to d cancel, you will get sigma h pd by 40, and because it is a sphere, in all directions this type of stress will be there. So in both the direction the same stress will be there, right? So in both directions, if we talk about the planar surface, same stresses will be there, right? And we are neglecting the radial stresses, right? So what type of condition will be there? The condition will be like this. So this is tensile stress, this is again tensile stress. Sigma h is given by PD by 40, same sigma h is given by here PD by 40, right? So on all directions we are getting sigma h, and that is PD by 40, right? So, and this is maximum as well as minimum residual stresses, both are same, right? And what will be the tau max then? Tau max, what will be the tau max here? That will be 0, that is sigma h minus sigma h by 0, right, by 2. So sigma h minus sigma h by 2, so this will be equal to 0. There is no shear stress developed in the material, only tensile stresses are there in the material, right? Only tensile stresses are there. isn't it? So these are the hoop stresses developed in the material, and that is same in both the directions, right? So what is then volumetric strain? What is then volumetric strain of the material? So volumetric strain, for volumetric strain, that the volume of the cylinder is given by volume, that is equal to 4 by 3 pi r cube. If r is the radius of this cylinder, we are talking about the radius now. Radius of this cylinder is r, 4 by 3 pi r cube. Then in this case, if v is a function of r only, so we can take dv, the change in volume, that will be equal to what will be that? That is 4 by 3 pi multiplied by 3 r square, right? So this is 4 pi r square, basically 3 r square means 4 pi r square. So dv will be equal to 4 pi r square, right? Change in volume is 4 pi r square. And if we divide both sides by v, dividing both sides by v, what we will get? We will get dv by v as 4 pi r square divided by 4 by 3 pi r cube, 4 by 3 pi r cube. So this will be come out to be dr. There dr will also be there, dr. So here dr term is also there. So this will come out to be 3 times dr by r, 3 times dr by r. So dv by v will come out to be 3 times dr by r. So this will imply that volumetric strain is 3 times the hoop strain, circumferential strain or hoop strain, right? So it means that volumetric strain is 3 times the hoop strain. So now we are talking about the volumetric strain. So we have obtained the result from there that volumetric strain is 3 times the hoop strain. But what is hoop strain? What is hoop strain? So what will be the value of hoop strain? So hoop strain will be equal to sigma h minus sigma by h by mu minus sigma h by e, in this direction, you can take any direction, minus mu sigma h by e, So this will be, hoop strain will be equal to sigma h by e 1 minus mu. This is our hoop strain, right? And sigma h value we know the value of sigma h. So what is the value of sigma h here now? So hoop strain will come out to be, that is equal to, put the value of sigma h is PD by 4T, so you will get PD by 4TE 1 minus mu. So this is the hoop strain, PD by 4TE 1 minus mu, right? Hoop strain. And put the value of this, you will get the volumetric strain. So hoop strain is 3 times the volumetric strain. So volumetric strain is 3 times the hoop strain. So you will get finally the volumetric strain as 3 times this value. So 3PD by 4T 1 minus mu. So this is the volumetric strain in case of spherical vessel, and this is important. This you have to remember. Direct formula will be used in few numericals, that this is 3PD by 4TE. 4TE, E should also be there, 4TE 1 minus mu. So this is the volumetric strain, and this is hoop strain. So hoop strain, volumetric strain, this both you should remember. Other than this, you should remember the stress, hoop stress. And hoop stress is same in both the directions, right? In case of spheres. So this was the case of thin spherical shells, the stress and strains in thin spherical shells.